Hey everyone, welcome back to physics. This will be lecture 2 of the course. So in this section we'll continue with our investigation of motion along a straight line by exploring the idea of instantaneous velocity. Let's go ahead and jump into it. So we'll call this section 1.2 instantaneous velocity. So in the last section we discussed average velocity. And average velocity is great for some questions. It's great for certain types of problems. Average velocity is totally adequate, but it doesn't really help us with questions like how fast was the car going at time t, right? So average velocity does not help us with questions like how fast was the car going at time t, right? So a very specific time, like 1 second into the race, how fast was the car going? The best average velocity can do is it can take some interval of time and it can figure out what the average velocity was over that interval. Right, now notice though that average velocity, well, really there are infinitely many ways that an average velocity can be resolved with instantaneous velocity. So for example, let's think of a car that has an average velocity of 100 meters per second over a 500 meter track. So assume a car has an average velocity of 100 meters per second over a 500 meter displacement. Right, so meaning, we start here at point 1, and then here's point 2, and this is 500 meters. And over that interval, the average velocity is 100 meters per second. Well, just notice there's infinitely many ways to accomplish that, right? So it could be the case that the car went 50 meters per second over the over the first half of the interval, then 150 meters per second over the second half of the interval. Right, so maybe it goes 50 meters per second here, and then it doubles its speed and goes 150 meters here. That would give you an average of 100 meters per second. Right, it may be the case that the car goes 90 meters per second for the first part of the track and then slows down to 10 meters per second, and you get this average of 50 meters per second. Right, it may have gone 200 meters per second, then maybe it goes negative 10 meters per second, and then 20 meters per second for some amount of time. The point is that the speed could be anything over that interval, right? The average velocity just tells us on average what it did over that 500 meters. But there's infinitely many ways to traverse 500 meters at 100 meters per second average velocity, okay? So that being the case, obviously in order to do precise physics kinds of experiments and problems, we'll need something a little more in the moment, so to speak, and that's where the idea of instantaneous velocity comes into play. Okay, so we're going to begin with our graph of position as a function of time. So we explored this last time in the last lecture. So again, we want to start with that. Okay, so let's say we've got our time axis and our position axis. And let's say we've got some position function. I'm just going to draw it like this, straight line. Okay. And so what we want to do is we want to consider equal allocations of time displacement here. So this will be our delta t. Now notice these are equally spaced, so that means it's the same interval of time repeatedly. Right, so you can think of this like maybe every hash is 2 seconds. So it's a 2 second interval, and then another 2 second interval, and another 2 second, another 2 seconds, right? And so you can think of these as, being as kind of driving this graph. Okay, and now the graph that I've drawn is one where velocity is constant. So if velocity is constant, meaning there's no acceleration, meaning that I'm going 50 meters per second at all the times, right? I never deviate from that velocity. If velocity is constant, then delta x, the displacement, is constant for a fixed delta t. What does that mean? Well, what it means is if you think about the displacement axis here, these delta x's are going to be constant as well, meaning they're all the same size. Right? So delta x's are all the same when your delta t's are the same. This is the case of constant velocity. Okay, so if velocity is constant, then delta x is constant for a fixed delta t. Let's take a look at what the picture looks like when velocity is not constant. Okay, so same setup here. I've got my time axis and I've got my position axis. Right, and again I'm going to just hatch off these delta t's. So this is delta t, so maybe the same 2-second intervals or whatever the time might be. Okay, and so on. Now, in a non-constant position, when velocity is non-constant, the position function is not a nice straight line like this. Instead, it's going to have it's going to have some curvature to it, right? So maybe it looks like this. And so you can probably tell what's happening with, so this one would be way up here, right? And so you can see what's going on with the delta x's in this case, right? They vary in size. So here's a delta x, here's a much smaller delta x, and here's a very small delta x, right? And this one up here extends off the graph, right? So this is the case of non-constant velocity. So if velocity is non-constant, then delta x changes relative to a fixed value of delta t. Okay, so your displacement varies over the same time interval. So in this initial 2 seconds, you weren't going very fast, so you didn't go very far. In this 2 seconds, you were going faster, so you went further. And indeed, you're speeding up here because you can see that delta x is getting larger and larger over the same time interval. Okay? All right, so this is kind of the two situations you can have. You can have constant velocity or you can have non-constant velocity. And this is the way it looks on the position graphs. Okay? Now, in the case of, well, let me just leave this up here for a second. In the case of constant velocity, right, in the case of constant velocity, instantaneous velocity is just equal to the average velocity. So in this case, instantaneous velocity is the same as average velocity. Hopefully that makes sense and is obvious, right? Because if you're going the same speed at all time, then any particular time I ask about what happened, how fast was the car going at 1.3 seconds? Well, it was going 50 meters per second. How fast was it going at 2 seconds? Well, it was going 50 meters per second. Why was it going 50 meters per second at all those times? Because it's constant. It's constantly going the same speed. So any particular time you select, the speed, the velocity is the same. Okay, so that's the case in constant velocity scenarios. But in non-constant velocity scenarios, if I ask you what the time is at a specific point, it's not going to be the average, right? It's going a lot slower here than it is over here, right? And so any point in between, it looks like in the case in this example, it's just going to be going with increasing speed, right? But it could, the position could change, the graph of the slopes could change, etc. But the point is, the takeaway here is that with non-constant velocity, we need to use something else. We need to kind of think about this from the standpoint of like calculus. In the case of non-constant velocity, we need to use calculus, right? We need to know the instantaneous rate of change, right? We need to know the instantaneous rate of change, right? Velocity is just the rate of change between position and time, of position relative to time. Right? And so we need to know the instantaneous rate of change, and that's really the derivative, isn't it? Okay. That's really the derivative. Now, I want people to be able to think about this intuitively from a geometric standpoint, though. So let's consider another example. So really, this is going to be the same picture. I'm just kind of shrinking it up because I'm going to do some, like a series of things to this. So here's your position 1, your position 2, right? And then you've got your times here, your delta t. Now, what happens if I zoom in on this picture? And so by zoom in, I mean I'm going to make the time interval smaller, and I'm going to bring my points closer together, right? So if I zoom in, okay, and pretend it's the same function, I'm just tightening up. I'm going to zoom into like this section, for example. Okay. So the interval of time is smaller. I've zoomed in on this somewhat. Now, what the point I'm trying to draw out here is that the curvature between point 1 and point 2 should diminish as you get closer and as they get closer and closer together. So if we zoom in again, right? So this time we're going to zoom in tight on this section, maybe. What's that going to look like? Going to look like that, isn't it? As we get closer, as P1 and P2 get closer and closer together, and the time interval delta t gets smaller and smaller, then even our non-constant position function, non-constant velocity position function, it begins to look like a straight line. So the closer and closer these two get together, the more straight the position function begins to look, right? So for non-constant velocity, we have to use the derivative, and really what we're doing is we're just zooming in on this graph. Now, as we zoom in on the xt graph, on the position graph, we can see that the graph of the line increasingly looks like a straight line, right? So as we zoom in on the position graph, we can see that the graph looks increasingly like a straight line. Okay, right? And so by making delta t arbitrarily small, right? So that's a notion from calculus. Hopefully you've seen the idea of the derivative in calculus. By making delta t arbitrarily small, the problem of non-constant velocity really reduces to the problem of constant velocity. The problem of non-constant velocity reduces to the problem of constant velocity. Meaning what? Well, meaning that the instantaneous velocity is really just the change in x divided by the change in t, right? And so we say that the instantaneous velocity, we'll denote it like this. This is really equal to the limit as delta t goes to 0 of the displacement, delta x, the change in x, divided by the change in time. Right, and we know from calculus that this is just dx over dt. Right, so what are we saying? Well, we're saying that the derivative of the position function, the position relative to time, the derivative of that function is the instantaneous velocity. Okay, very nice. Right, so the derivative of position is velocity. And hopefully that makes sense because, you know, velocity is just the change in position relative to the time. So let's do an example. Let's do an example kind of bringing a bunch of this together. Okay. So we'll again use the idea of a car moving in a idealized straight line motion, right? So a car's position varies with time according to the equation. So now we've got an equation for this. X of t equals 20 meters, so the starting position is 20 meters, plus 5.0 meters per second squared times t squared. Okay, so the idea here is I plug in a time, and what I get out of it is the position of the car. And again, it's just the distance from the origin. Okay, so we've got 4 parts to this question. First thing we want to know is we want to find the displacement, delta x, between t equals 1 second and t equals 2 seconds. So basically evaluate the position at those 2 time intervals and figure out the displacement. Part B, let's find the average velocity over this interval. T equals 1 second to t equals 2 seconds. Part C, let's find the velocity at 1 second. So this is part C. Find the instantaneous velocity at t equals 1 second, but we're gonna kind of approximate it. So we're gonna approximate the instantaneous velocity by considering a very narrow interval of time around t equals 1 second. Okay. And then part D, let's derive an expression for instantaneous velocity. So we want to find velocity as a function of time. Okay. All right. Cool. Let's do this. Let's calculate these examples. Let's work through this example. So part A, again. So our expression is this: xt equals 20 meters plus 5.0 meters per second squared times t squared. Okay, so that's our expression. Part A, remember, we're looking for the displacement between 1 second and 2 seconds. So we really just need to calculate these values. Okay, so what's the position at 1 second? Well, you just plug in 1 second into the position function. It tells you 20 meters plus 5.0 meters per second squared times 1 second squared. Okay, and so you get 20 plus 5, basically. I could just put 25 here. So 25 meters. Now notice the seconds will cancel out and you're left with 20 meters plus 5 meters. So then we need to know the same thing for x equals 2 seconds. So again, 20 meters plus 5.0 meters per second squared times 2 seconds. Okay, now what happens here? Well, I've got 20 meters up front here. The seconds cancel. I've got 5 times 4, which is 20. So 20 plus 20 is 40. Okay. So my displacement then, delta x, is equal to my ending position minus my starting position. So that would be x of 2 seconds minus x at 1 second. So 40 meters minus 25 meters, right? And I get, what, 15 meters. Okay, so that's part A, just that displacement. Now part B, we're asked to find the average velocity over this time interval. So we want the average velocity. All right, remember that's delta x over delta t. So delta x is x2 minus x1, and delta t is t2 minus t1. x2 is 40 meters. x1 is 25 meters. t2 is 2 seconds, and t1 is 1 second. So this is 15 meters over 1 second. So this is 15 meters per second. Okay, so our average velocity between 1 and 2 seconds was 15 meters per second. All right, very good. Now, part C is the somewhat, probably maybe the trickiest part of this example. And part C says find the instantaneous velocity at t equals 1 second. But the way we want to do is we want to take a very narrow slice, very narrow interval around 1 second, right? So you can think of it like this. Here's my t equals 1 second, right? And then maybe here's t equals 2 seconds, and here's t equals 0 seconds. So rather than use 0 to 2 or 1 to, what I want to do is I want to find a very narrow slice, right? And use that as my delta t. Okay, so what I'm going to recommend we use is 0.95 seconds and 1.05 seconds. So really close around 1 second. It's probably a good idea to center it on 1 second too. Okay, and then what we want to do is we just want to find the average velocity over this very small interval of time, and that should be a good approximation to the instantaneous velocity. And then we'll check it in part D. Okay, and so to do this, we need delta x over this small interval, right? So we're going to need the position function evaluated at this side, 0.95 seconds. So x of 0.95 seconds. Right, so you may need a calculator for this one, and the math gets a little bit more involved. So 5.0 meters per second squared times 0.95 seconds squared. Now, just go grab a calculator, plug all that in, and you'll see that the velocity is about the position is about 24.5125 meters, roughly. Now, give yourself a lot of digits here, because I think you may need them sometimes for these kinds of problems. And then the other position is the endpoint, which is 1.05 seconds. So x of 1.05 seconds. So 20 meters plus 5.0 meters per second squared times 1.05 seconds squared. Now, again, plug all that into a calculator, and what you'll see is you get something like 25.5125 meters. Okay, so this tells you your displacement. You basically went 1 meter. Okay, and so the velocity, the instantaneous velocity at t equals 1 second is approximately the average velocity in this case, because it's a very narrow interval. And the average velocity would be 25.5125 meters minus 24.5125 meters divided by 1.05 seconds minus 0.95 seconds, right? And if you do the subtraction up top, you get 1 meter, and if you do the subtraction on the bottom, you get 0.1 seconds. And so when you divide that out, you see 10 meters per second, right? So the instantaneous velocity is approximately 10 meters per second. Okay. Now, it may be the case that if you make this delta t even smaller, like maybe 0.99 seconds and 1.01 seconds, so make it really close, you might get a different answer. You might get the same answer, you might get a different answer. It just kind of depends on the underlying position function and what's actually happening over that interval. Okay, so now the last part of the problem is to derive an equation for the instantaneous velocity. Okay, so remember, we've got our position function, and our position function was 20 meters plus 5.0 meters per second squared times t squared. Now we want to derive an equation that tells us the velocity for any time, right? And so we just got done talking about that. The velocity as a function of time is equal to the derivative of the position function. Right, so this is the expression we would need. So we're given the position function. We're given the position as a function of time. We can calculate the velocity as a function of time by differentiating that position function. And so we need the derivative of 20 meters plus 5.0 meters per second squared, t squared. Now, this is the derivative with respect to t. There really is only one variable, and that's t. And so in the case of this derivative, of course, 20 meters becomes, that's just a constant, so that's zeroed out. And so we get 0 for this. And this is 5 meters per second squared. And then t, when we differentiate t squared, we get 2t. Right, so this really becomes 10 meters per second squared times t, right? So v as a function of time is equal to 10 meters per second squared times time. Okay, and so we can check our approximation. This will tell us the instantaneous velocity for any second, for any time you plug into this, right? So if we want to know the instantaneous velocity at 1 second, we could evaluate this at 1 second, and it would just be simply 10 meters per second squared times 1 second. Right, now notice one of the seconds cancel and the units are consistent. You get 10 meters per second, right? Which is exactly what our approximation resulted in. Okay, so perfect. Okay, perfect. So that's a great example, a good place to end this section. And in the next section, we'll extend these results, the idea of average and instantaneous velocity. We'll extend that to average and instantaneous acceleration. We'll see you then.